If you ever sat in physics class from one of these bad boys, tell it all about wave-particle duality. All particles make waves and waves make particles. Take light for example. It travels through space as a wave, but also collides with other objects as a particle. But what does that make light? Have you ever stopped thinking about what that really means? What makes matter waves like a particle or as a wave? Thomas Young's famous double-slit experiment showed that when a photon beam is aimed at two narrow slits, a pattern of alternating dark and light bands are formed. This must be a result of light diffracting through the slits and interfering to produce the pattern, both properties of waves. But is there a way to show its particle nature? We can see the wave nature in the interference and the diffraction, but to witness the particle nature, we need to know the trajectory of each photon, that is, the path it takes. Let's use a camera to track the direction the photons take. If we record footage of the experiment, we know which slit the photon passes through, and the path it takes. But when we look back at the recording, to our surprise, the interference pattern and evidence of light's wave nature has disappeared. By taking a photo of each photon, we split the light beam up into two categories, slit A and slit B. As a result, the light from each photon travels only through its slit, forming the two lines as particles do. Since light is no longer being perceived as a wave, no interference, and therefore no interference pattern occurred. So we are perceiving this light as a wave, but our camera is perceiving it as a particle. So what does that make this light, wave or particle? This is one of the most prominent examples of the observer effect, the idea that the observation or measuring of a situation can change the result. By measuring it, you force light to behave as a wave. Similarly, the camera's measurement forces it to behave as a particle. Without an observer, there is no way to obtain a result, and therefore no result that has any meaning. The most mind-blowing thing about this is that even though we never came in direct contact with the system, the mere act of observing it, or changing our mode of observation, caused a fundamental shift in its behavior. This doesn't apply at a high level of physics. When you do something like measuring the temperature of a glass of water, the mercury must change its state through absorbing or releasing heat energy, which changes the temperature of the water. Small discrepancies like these, however, are probably the result of incorrect measurement methods. The cause of the double-slit experiment, on the other hand, is a lot more interesting. In quantum mechanics, an object exists in several states at once, that is, a superposition. The superposition can be described using a wave function, which statistically predicts the object's trajectory. However, our observation reduces the possibilities for trajectory down to just one, which collapses the wave function. So to conclude, observation affects outcome. And so you know that we'll never really be able to perceive the world as it really is, not without changing it at some quantum fundamental level. But at the same time, it's a little comforting to know just by existing and observing, we shape the universe itself.